In February of 2026, a buoy in the North Atlantic recorded something that made oceanographers check their instruments twice. The water at that location was colder than it had been 100 years earlier. Not warmer, colder. And this was happening against the backdrop of the warmest ocean ever measured by satellites. At almost the same moment, in the northeastern Pacific, satellites picked up a mass of warm water covering 10 million square kilometers, larger than the entire land area of Canada. Scientists gave it a name, NEP-25A. It stretched nearly 9,000 miles, and some researchers were already comparing it to the legendary Blob of 2014, an event once dismissed as a one-off anomaly. Today, warm water masses like it are showing up almost every year. A cold patch off Greenland, a colossal warm mass in the Pacific, an ocean that has already absorbed more than 90% of the planet's excess heat. It is behaving in ways that climate models from just 10 years ago never predicted. What is happening to the largest climate machine on Earth? This is not a film about global warming. Temperature is only one symptom. This is a film about something else, about mechanisms, about how the ocean actually works underneath the surface, what drives it, and why, in 2026, several independent research teams, from the Potsdam Institute to the Scripps Institution of Oceanography, are saying that some of these mechanisms are starting to behave differently than expected. The ocean hasn't broken, it's still doing its job, but its inner workings have become the subject of one of the most intense scientific investigations of the past decade. And to understand what's happening, we'll need to descend 2,000 meters below the surface, rise into orbit alongside the satellites, dig through archives 1,000 years old, and look inside the mathematical models trying to predict what comes next. Let's start with the most basic question. Why does the ocean control the planet's climate at all? People tend to think of the ocean as scenery, a blue surface under an open sky. But in reality, the ocean is a heat battery on a planetary scale. Water holds 4 times more heat than air of the same volume. Because of this single property, the top few meters of the ocean store as much thermal energy as the entire atmosphere of Earth combined. When the sun heats the planet, most of that energy doesn't stay in the air. It goes into the water. By various estimates, the ocean absorbs more than 90% of the excess heat generated by rising greenhouse gas concentrations. Without that, average air temperatures on Earth would already be tens of degrees higher, not fractions of a degree as they are now. For a very long time, the ocean has acted as a buffer, softening climate change and stretching it out over time. But absorbing heat is only step one. That heat has to go somewhere. And this is where the most interesting part of the story begins. The story of a global system of currents that works like a planet-sized pump. Picture a giant conveyor belt running through every ocean on Earth. Warm water at the equator moves north, releases its heat into the atmosphere, cools, becomes denser, sinks, and returns to the equator as a cold, deep current. Scientists call this thermohaline circulation. Circulation driven by temperature and salinity. For thousands of years, this system has redistributed heat between the poles and the equator, making Earth's climate hospitable to complex life. One of the key branches of that conveyor belt is the Atlantic Meridional Overturning Circulation, or AMOC. It's a system of currents that includes the famous Gulf Stream, carrying warm water from the tropics into the northern Atlantic. AMOC is the reason northwestern Europe's climate is so much milder than other regions at the same latitude. Without it, winters in London or Oslo would be far harsher. And it's precisely around AMOC that one of the most intense scientific debates in all of climatology has been unfolding in recent months. This mystery didn't begin yesterday. Back in 2021, researchers noticed a strange region in the North Atlantic, south of Greenland and Iceland, that they called the cold blob, or the warming hole. An ironic name, since the water there is actually anomalously cold, while the rest of the ocean warms around it. While the whole world was heating up, this one patch had been cooling for over a century. For a long time, scientists debated what was causing that cooling. One hypothesis, a simple local loss of surface heat due to shifting winds and cloud cover. The other, more troubling hypothesis, a direct signal that AMOC itself was weakening. In 2026, a study emerged that tipped the scale toward the second hypothesis. The research, cited by CNN and other major outlets, showed that the cold blob isn't a quirk of atmospheric circulation. It's a consequence of a slowing deep ocean circulation. David Thornalley, a professor of ocean and climate science at University College London, noted that the study strengthens the link between the cold blob and a weakening AMOC, though he cautioned that the sparse, real-world data available means it's too early to speak with full certainty. This is a genuinely important point. In ocean science, clear-cut answers are rare. There are confirmed observations, there are working hypotheses, and there are questions still under investigation. The cold blob itself is a confirmed observation. Its connection specifically to a weakening AMOC is still a hypothesis, one gathering more and more support, but not yet an established fact. So what do direct measurements of the circulation itself actually show? Since the 2000s, an array of sensors called RAPID has been operating across the Atlantic at 26 degrees north latitude, a network of mooring stations continuously measuring the transport of water at different depths. It's one of the few tools that provides not a model estimate, but a real, direct measurement of the current's strength. RAPID data published in 2026 showed a steady, statistically significant decline in water transport in the deep western branch of the circulation. From 2004 to 2023, the decline amounted to roughly 2.6 sverdrups per decade. Scientists measure the strength of ocean currents in sverdrups, where 1 sverdrup equals 1 million cubic meters of water per second. That means the overall strength of the circulation has dropped from around 20 sverdrups to about 15, a decline of nearly a quarter in 20 years. 20-some years of observation is a very short window by the standards of a climate system that operates on the scale of centuries and millennia. That's why scientists are searching for additional, longer-running indicators, so-called AMOC fingerprints, in other ocean variables for which longer data records exist. One such fingerprint is water temperature at depths of 1,000 to 2,000 meters in the equatorial Atlantic. Models show that a weakening AMOC causes warming specifically at these depths. A study by Ren, Shi, and colleagues published in 2025 found sustained warming of mid-depth waters dating back to 1960 that broke from natural variability in the early 2000s. By the author's estimate, this corresponds to an AMOC slowdown of roughly 2 sverdrups since the mid-20th century. Then, in April 2026, Science Advances published a paper by Valentine Portman and colleagues at the French research center INRIA. They combined observations across several independent variables, rather than relying on a single direct metric, to produce a more precise estimate of future weakening. Their conclusion? By the end of the century, AMOC could weaken by roughly 50%. That's notably higher than the average estimate from the previous generation of climate models, which put the weakening at around 32%. Portman explained the logic behind the approach simply. The point was to use more information across several variables simultaneously, because AMOC is a very complex system that depends on multiple processes at once. That's a meaningful shift, not leaning on a single variable, but looking at the system as a whole. There's a third line of evidence too, direct observations of consequences already underway. A study by federal U.S. climate researchers, published in 2025, found that the current's weakened phase has already contributed to increased flooding along the northeastern U.S. coast, accounting for as much as half of all flood events since 2005. The physics behind this is fairly simple. As the circulation weakens, sea level along the eastern coast of North America rises faster because the current is no longer pulling water northward with the same force. Stefan Rahmstorf, a physical oceanographer at the Potsdam Institute for Climate Impact Research and head of one of the leading research teams on this topic, called the new results very concerning. According to him, confidence has grown in a scenario where the world approaches a tipping point for AMOC as early as mid-century, with a possible collapse by 2100. An AMOC shutdown is no longer a low-probability event, he said. That said, it's worth bringing the conversation back to calmer ground. Even in the most alarming scenarios, we are not talking about a sudden, catastrophic shutdown in the next few years. The Intergovernmental Panel on Climate Change, in its 6th assessment report, rates the probability of an abrupt AMOC collapse before 2100 as very unlikely, while still acknowledging it as a low probability, high-impact risk that cannot be fully ruled out. More conservative models, using high-resolution eddy-resolving ocean simulations, suggest that AMOC's response to Greenland meltwater over the 21st century could be significantly weaker than older, coarser-resolution models assumed. In other words, the scientific community is far from unanimous about the pace of change, and that's exactly what makes AMOC research such a compelling, active field right now. Here's what we know for certain. The circulation is weakening, and that's confirmed by direct measurements over the past 20 years. What remains a hypothesis: the scale and pace of further weakening, and the probability of an abrupt shift into a new state. What's being studied right now? The connection between the cold blob, deep temperature anomalies, and the circulation's actual strength. The ocean hasn't stopped, but one of its most important pumps is working differently than it was expected to just 10 years ago. While the Atlantic surprises scientists with its cold patch, the Pacific is delivering the opposite surprise: record-breaking heat. To understand the scale of what's happening, we need to go back to 2014. That year, the northeastern Pacific saw the first-ever recorded appearance of a massive zone of anomalously warm water, which researchers jokingly nicknamed the Blob. It lingered until mid-2016 and became one of the most studied climate events of the decade. Mass sea lion die-offs, crab fishery closures, and toxic algal blooms all along the west coast of North America. At the time, it was considered a once-in-a-century anomaly. But since then, events like it have started recurring with unsettling regularity. In September 2025, the northeastern Pacific reached its highest average temperature on record, 20.6 degrees Celsius. NOAA scientists noted that this was only the third time on record that such a large section of coastal ocean had stayed this warm for this long, and this time without any help from El Niño. By May 2026, things had gotten even more extreme. Satellites detected a new heat event, designated NEP25A, that grew to nearly 10 million square kilometers, becoming the largest marine heat wave in the northeastern Pacific since 1982, when systematic satellite measurements of sea surface temperature began. The event stretched almost 9,000 miles from the coast of North America deep into the tropical Pacific, past the international date line. And here's what's especially interesting. This time, the ocean heat wave wasn't a consequence of El Niño. It came first, and according to several researchers, it may itself be feeding into the development of a future El Niño, supplying it with energy from an already heated surface layer. So what exactly is El Niño, and why does it matter so much for understanding the planet's climate machine? El Niño, the Southern Oscillation, is a natural cycle of ocean-atmosphere interaction in the tropical Pacific. Under normal conditions, trade winds push warm surface water westward toward Indonesia and Australia, while cold, nutrient-rich deep water rises along the coast of South America. During El Niño, the trade winds weaken, warm water sloshes back eastward, and the entire system of heat exchange between ocean and atmosphere shifts, with consequences for weather on virtually every continent. According to NOAA's Climate Prediction Center, by the summer of 2026, the probability of El Niño forming was estimated at 82% for the May through July window, rising to 96% by the winter of 2026 to 2027. Sea surface temperatures off the California coast were among the warmest ever recorded for this time of year, rivaled only by the powerful 1997-98 El Niño and the 2014-15 warm blob years. By the end of June 2026, monthly anomalies in the key Niño 3.4 region had reached plus 1.24 degrees Celsius, well above the threshold for the phenomenon to form. Forecast models put the odds of El Niño persisting through the rest of the year at 97 to 98%. At the same time, the world's oceans as a whole recorded their highest average surface temperature ever measured for the month of June. Parts of the Mediterranean were nearly 6 degrees above the long-term average. Parts of the North Sea were 3 degrees above normal. It's worth understanding the mechanics of what happens next. A typical El Niño cycle lasts about a year, and its full effect on global air temperature shows up closer to the end of the cycle, not at the start. That means if the event now forming does develop into a strong or even super El Niño, it likely won't be this year, but next year that becomes the hottest year on record. Just as happened following the El Niño events of 2015-16 and 2023-24. Over the past 2 years, scientists have significantly improved their ability to forecast marine heat waves 3 to 4 months in advance in places like Australia and the United States. Early forecasts let fisheries managers reduce allowable catch limits ahead of time and launch protection programs for vulnerable species before a heat wave even peaks. There's a worrying wrinkle, though. Several researchers point out that funding cuts to climate observation networks over the past year, along with the weakening of certain atmospheric research institutions, could jeopardize this forecasting progress at precisely the moment when forecast accuracy matters most. Climate Impact Company, which specializes in analyzing marine heat waves, estimated in April 2026 that global marine heat wave coverage stood at 27% of the world's ocean surface, with projections of growth to 40%, possibly 45%, by the third quarter of the year, largely driven by the forming El Niño. Beyond NEP 25A, researchers point to intensifying heat waves in the Mediterranean, in the Norwegian Sea, in the so-called North Atlantic warm hole south of Greenland, and to 5 separate large heat anomalies in the southern hemisphere, from the Argentine coast to the southern Indian Ocean. That raises the question climatologists care about most. Are marine heat waves like these becoming the new normal rather than an exceptional event? The honest answer, for now, is still under study. Statistically, because of the ocean's long-term warming trend, the frequency of temperatures crossing fixed historical heat wave thresholds is bound to rise over time, even without any new mechanism at play. If you strip out that long-term warming trend from the calculation, the statistics look considerably calmer. But the rising frequency, intensity, and, crucially, duration of these heat waves, something some oceanographers have started calling supermarine heat waves, is forcing a rethink of the very methodology used to define them. To understand how the weakening of one current system and the intensification of heat waves can affect weather thousands of kilometers away, we need to look at the most intimate process linking ocean and air: evaporation. Every second, billions of tons of water vapor rise from the ocean's surface into the atmosphere. This process doesn't just add moisture to the air, it transports a staggering amount of energy. Physicists call this the latent heat of evaporation. Turning water into vapor requires energy, and that energy stays hidden inside the vapor molecules until they condense back into droplets somewhere in the atmosphere, releasing their heat there, sometimes thousands of kilometers from where the evaporation happened. This is exactly why tropical storms and hurricanes draw their destructive power from warm ocean water. The warmer the sea surface, the more energy is available to a developing storm. When a tropical cyclone passes over a marine heat wave zone, like NEP25A, or the heat anomalies in the Caribbean basin, it picks up an extra reserve of energy and can intensify faster than standard forecast models predict. This isn't a hypothetical connection. Researchers tracking marine heat waves in the Gulf of Mexico and the Caribbean Sea in previous years warned directly that developing tropical storms passing through already heated waters face an elevated risk of rapid intensification. But the relationship between ocean and atmosphere also runs in reverse, producing much slower and much larger scale effects, shaping cloud cover and atmospheric circulation across entire hemispheres. Scientists studying the North Atlantic wormhole and the intensifying Mediterranean heatwave found a pattern. Over the past 10 years, the combination of these two anomalies has been linked to the formation of a powerful summer high-pressure ridge over Europe on 7 separate occasions. Such a ridge blocks the usual movement of air masses, traps hot, dry air over the region, and can turn an ordinary summer into a prolonged heat wave. That brings us to one of the most actively discussed topics in atmospheric science today: the possible link between changes in the ocean and the behavior of the jet stream. Those fast-moving rivers of air roughly 10 kilometers up that steer the paths of storms, high-pressure systems, and entire weather patterns across the mid-latitudes. The jet stream exists because of the temperature difference between the tropics and the polar regions. The greater that temperature difference, the stronger and more stable the jet stream, and the more directly it runs from west to east. But if the polar regions are warming faster than the tropics, which is exactly what's been happening in recent years, that temperature contrast shrinks, and the jet stream can theoretically become slower, wavier, and prone to forming stalled loops in which the same weather, heat, rain, or cold, parks itself over one region for an unusually long time. Here, it's worth adding an important caveat that climatologists keep repeating. The link between Arctic warming and jet stream behavior remains one of the most actively debated and least conclusively proven topics in modern atmospheric science. Some research groups find statistical support for a trend toward a wavier jet stream and more frequent blocking patterns. Other groups, analyzing the very same data with different methods, find no signal strong enough to distinguish from the atmosphere's natural variability. This is an open scientific question, not an established fact, and any honest documentary is obligated to state that uncertainty plainly. Within this whole system, the ocean plays the role of a slow, inertial partner. The atmosphere changes over hours and days. The upper ocean changes over months. The deep ocean and large circulation systems, like AMOC, change over decades and centuries. That's why the ocean functions as a kind of memory for the climate system. Changes happening in the ocean today may not show up in the weather for years, sometimes decades. There's another channel of influence that gets discussed less often: cloud cover. A warmer ocean surface evaporates more moisture, and in theory, more moisture in the atmosphere means more clouds. But clouds come in different types. Low, thick clouds reflect sunlight back into space and cool the planet, while high, thin, cirrus clouds do the opposite, trapping outgoing heat radiation like a blanket. The balance between these two cloud types in a changing, warmer ocean remains one of the biggest sources of uncertainty in every current climate model. Scientists at the National Center for Atmospheric Research and Europe's ECMWF acknowledge that cloud feedback remains the single largest source of disagreement between different models' warming projections. That's precisely why satellite observation of the ocean is just as important today as observation of the atmosphere itself. Right now, an entire constellation of satellites, from NASA and NOAA missions to Europe's Copernicus program, is measuring daily sea surface temperature, sea surface height, wind speed over the water, and chlorophyll concentration, which indicates phytoplankton activity. Each of these parameters is one more piece of a single enormous puzzle. Exactly how the ocean is exchanging energy with the atmosphere right now in real time. While most attention stays fixed on the ocean's surface, a much quieter, much less visible drama is unfolding at depth. The ocean doesn't just store heat, it stores oxygen, a dissolved gas without which the vast majority of marine organisms, from tiny zooplankton to large predatory fish, cannot survive. And over the past 50 years, the ocean's oxygen content has been steadily declining. According to the International Union for Conservation of Nature, the global ocean has already lost about 2% of its dissolved oxygen since the 1950s, and if current trends continue, that loss could reach 3 to 4% by 2100. That sounds like a small number, but the scale of the world's oceans is such that even those percentages represent staggering volumes of water becoming less and less hospitable to life. The mechanism behind this is relatively simple, and in that sense, it's one of the best understood aspects of the changes underway in the ocean. Warm water physically holds less dissolved gas than cold water, the same reason warm soda goes flat faster than cold soda. On top of that, warming surface layers become lighter, while colder, denser water underneath becomes relatively heavier, which makes it harder for layers to mix and prevents oxygen from the surface from reaching depth. Calculations published in Nature Communications reveal something particularly troubling about the system's inertia. Even if carbon dioxide emissions stopped completely today, the deep ocean would still lose more than 10% of the oxygen it held before the industrial era began. About 80% of that committed oxygen loss will occur below 2,000 meters, where slow circulation means the water will remain there for centuries, continuing to lose oxygen even after the rest of the climate system has otherwise stabilized. How tangible is this for living organisms? A study published in 2025 by a team from the Autonomous University of Barcelona offered one of the clearest answers yet. Researchers examined fossil remains of lanternfish, small deep-sea fish of the family Myctophidae that live in the ocean's twilight zone, at depths between 200 and 1,000 meters, preserved in seabed sediments in the eastern Mediterranean spanning more than 10,000 years. Despite their modest size, these fish have a combined biomass of roughly 600 million tons, possibly making them the most abundant vertebrates on Earth by weight. The fossil record showed that during past periods of severe deoxygenation, lanternfish populations collapsed sharply and only recovered once oxygen levels rose again. The case of the lanternfish clearly illustrates what could happen on a much larger scale if ocean deoxygenation continues. If a group with this much biomass disappears, other marine species are likely at risk too, warned Sven Palix, the study's lead author. The ocean's twilight zone, where these fish live, plays a key role in the planet's climate system. It's where much of the so-called biological carbon pump takes place, the process by which organic carbon accumulated by plankton near the surface sinks into the depths and gets locked away from the atmospheric cycle for a long time. Changes in this zone aren't just a matter of survival for individual fish species. They're a matter of how effectively the ocean will continue absorbing carbon in the future. A similar but far more visible drama is unfolding closer to the surface on coral reefs. In April 2024, NOAA, together with the International Coral Reef Initiative, officially confirmed that the planet was experiencing its fourth global mass coral bleaching event on record, the second in the past 10 years. From early 2023 through mid-2025, heat stress capable of triggering bleaching affected roughly 84% of the world's coral reef area across 3 ocean basins: Pacific, Atlantic, and Indian. Mass bleaching was documented in at least 83 countries and territories. For comparison, the previous record, set during the third global event of 2014 to 17, was 68.2%. Bleaching isn't the same as death. When water gets too warm, a coral polyp expels the microscopic algae living in its tissue, the same algae that give coral its vivid color and most of its energy through photosynthesis. The polyp stays alive but turns pale, weakened, and far more vulnerable to disease. If the stress recedes quickly enough, the algae can return and the reef can recover. If heat stress lasts too long or recurs too often, the coral dies. In June 2026, NOAA formally announced that the fourth global bleaching event most likely ended in 2025, after an entire Australian summer passed without new reports of large-scale bleaching anywhere in the world. An event in Western Australia in early 2025 appears to have been the final chapter of that wave. But the reprieve may be short-lived. The El Niño forming in 2026 is once again raising surface water temperatures in the tropics, and NOAA's 4-month bleaching risk outlook already shows elevated danger for much of the North Pacific, including Hawaii, as well as for Florida and the Caribbean this coming summer. Some researchers are framing the question even more starkly, wondering whether this could be the year certain heat-sensitive coral species cross a point beyond which recovery simply becomes impossible, a kind of local point of no return. At the same time, encouraging examples keep accumulating. The Mesoamerican Reef, stretching nearly 1,000 kilometers along the coast of Mexico and Central America, lost as much as 40% of its area during the 2024 bleaching event, but some sections showed notable recovery, largely thanks to improved fisheries management and rebounding populations of algae-eating fish that would otherwise smother a weakened coral. That's one of the most important takeaways from the story of coral reefs. A reef's fate isn't determined by water temperature alone. Local factors, pollution, overfishing, coastal development, determine how resilient a reef will be in the face of heat stress. Reducing those local pressures genuinely helps reefs recover faster, even as global temperatures continue to climb. How do scientists even know what's happening in a body of water too vast and too deep to observe directly? The answer lies in one of the most underappreciated scientific programs of our time, one that operates almost invisibly to the general public. It's called the Argo program, named after the mythical ship from the Greek legend of the Argonauts, a name chosen deliberately to highlight its connection to the Jason series of satellites which measure sea surface height. Today, nearly 4,000 autonomous floats drift across every ocean on the planet. Each float follows a 10-day cycle. It sinks to a depth of about 1,000 meters, drifts there with the current for 9 days, then dives deeper still to 2,000 meters and begins a slow rise back to the surface, continuously measuring temperature, salinity, and pressure the entire way up. Once it reaches the surface, the float transmits its collected data to a satellite, then sinks again to begin the next cycle. This network, working in tandem with satellite altimetry, measuring sea surface height from space, has, for the first time in history, given scientists the ability to see how the heat content of the entire world ocean is changing in something close to real time, rather than relying on scattered point measurements from ships, as was the case for nearly the whole 20th century. Right now, the program is entering its next stage of evolution. A new generation of floats, known as Deep Argo, is being developed and tested, capable of diving to depths of 6,000 meters, covering essentially the entire volume of the ocean, including its deepest trenches. Other new models are being equipped with biogeochemical sensors that measure oxygen content, water acidity, nitrate concentration, and even the intensity of light penetrating the water column, directly relevant to phytoplankton activity and the biological carbon pump discussed earlier. One of the practical tasks this expanded observation network is tackling is monitoring the South Atlantic, far less studied than its northern counterpart, but playing a crucial role in understanding the variability of the entire overturning circulation system. Scientists combine satellite altimetry, Argo measurements, and wind data to reconstruct a three-dimensional picture of currents in places where they once had to rely on rare, expensive research vessel expeditions. There's a less obvious but critically important challenge in all of this: reconciling data from different instruments with one another. Scientists studying the global sea level budget note that since 2016, there's been a small but persistent discrepancy between the independently measured rise in sea level and the sum of all its known contributors: glacier melt, thermal expansion of water, changes in land water storage. Part of that discrepancy is explained by gradual drift in individual Argo float sensors, part by possible drift in the satellite altimeters themselves, and part is likely tied to insufficient observational coverage of the deep ocean, especially in the southern hemisphere. This is a textbook example of a question still being studied, and one that vividly illustrates just how difficult it is to maintain measurement accuracy across a system this vast over decades. Beyond the autonomous floats, an entire fleet of other instruments tracks the ocean's condition in real time. The National Data Buoy Center collects information from 1,300 observation stations worldwide. Satellites in the JASON series and their successors measure sea surface height with centimeter-level precision, allowing scientists to track current circulation and even the ocean's own slow volume changes from warming water. Specialized satellites, like those in the European Union's Copernicus program, measure sea surface temperature, chlorophyll concentration, and sea ice thickness nearly every day. And deeper still, where no autonomous float can go without risking being crushed by pressure, remotely operated and autonomous underwater vehicles do the work. The same machines that explore hydrothermal vents, map unknown seamounts, and collect water samples from the darkest, coldest corners of the ocean, places where neither light nor often oxygen itself can reach. Together, all these instruments, floats, buoys, satellites, ships, underwater vehicles, form what oceanographers call the Global Ocean Observing System. It isn't a one-time project, it's a continuously operating infrastructure, gathering millions of data points every single day. It's precisely because of this infrastructure that we can even ask questions about what's happening with AMOC, with marine heat waves, or with oxygen levels at depth, and get answers grounded not in guesswork, but in evidence. To really understand why scientists are watching AMOC's slowdown so closely, we need to look much further back than the last 20 years of satellite data. Climate archives, Greenland ice cores, Atlantic seabed sediments, corals that have stored a chemical memory of past centuries in their skeletons, tell a story that seems almost unbelievable at first. During the last ice age, tens of thousands of years ago, the climate of the northern hemisphere underwent sudden temperature swings known as Dansgaard-Oeschger events. Within a matter of decades, sometimes just a few years, Greenland's temperature could jump by 8 to 16 degrees Celsius, a colossal leap by the standards of the climate system. Many of these abrupt warmings are believed to have ended in so-called Heinrich events, when massive streams of icebergs broke off the Laurentide ice sheet that existed at the time, dumping fresh water into the North Atlantic. Why does this matter? Because a similar mechanism is considered today to be one of the key risks facing the modern AMOC. An influx of large volumes of fresh, less dense water into the North Atlantic, whether from the Greenland ice sheet in the past or its melting ice cover today, can disrupt the sinking of cold, salty, dense water that drives the entire deep conveyor belt of circulation. If that sinking process weakens or stops, the whole system loses one of its main engines. That's exactly why, in October 2024, 44 climatologists signed an open letter stating that, based on studies from recent years, the risk of an AMOC collapse had been seriously underestimated, and that such an event could occur within the coming decades, with devastating consequences, especially for the countries of Northern Europe. The scientists urged Nordic governments to ensure implementation of the Paris Agreement with this risk specifically in mind. That letter sparked considerable debate within the scientific community, not because anyone denied that AMOC was weakening, but because estimating the probability and timing of an abrupt collapse remains one of the most uncertain quantities in all of climate science. A preprint study published in January 2026 using high-resolution modeling suggested that an AMOC collapse could be significantly more likely than previous generations of models assumed, due to the system's higher-than-expected sensitivity to meltwater input. At the same time, the multi-model ensemble from the 6th phase of the Coupled Model Intercomparison project, the very set of models underlying the latest IPCC report, offers a far more measured picture on average. An AMOC weakening of 34 to 45% by 2100 under a high emissions scenario, corresponding to a transport reduction of roughly 6 to 8 sverdrups. These models rate an abrupt collapse before the end of the century as highly unlikely, while acknowledging they can't rule it out entirely, characterizing it as a low probability, potentially very high impact risk. Another study, published in Environmental Research Letters in 2025, pushed past the standard modeling horizon of 2100 and extended calculations beyond it. The result was telling. Under a high emissions scenario, AMOC collapse occurred in 67% of model runs after 2100, and in 30% of runs under a moderate emissions scenario. This highlights an important methodological point. If you stop modeling right at the turn of the century, you can miss processes that keep developing past that arbitrary cutoff. It's worth pausing here to separate what science has genuinely established from what remains a matter of active dispute. Established with high confidence, AMOC will weaken during the 21st century under any realistic emissions scenario. This is a robust result across nearly every modern climate model, regardless of the scenario used. Established by direct measurement, an actual, ongoing slowdown of the circulation's deep branch recorded by the rapid array over the past 20 years. Still a matter of debate, the precise scale of that weakening by century's end. Estimates range from roughly 30 to roughly 50%, depending on the method used. Still a matter of active scientific dispute, the probability of an abrupt, nonlinear collapse of the circulation before 2100. The IPCC report rates that probability as low, with medium confidence in the rating itself, a formulation that, on its own, reflects just how much uncertainty surrounds this question. It's exactly this layered set of estimates, not a single yes or no, but a spectrum of probabilities carrying different degrees of scientific confidence, that makes AMOC research such a telling example of how climate science actually works. It isn't a stack of finished predictions. It's a living, constantly refining process where every new study either narrows the range of uncertainty or, sometimes, opens up new questions that weren't visible before. For a long time, MOC was studied as a single, relatively isolated system. A growing body of research shows that's no longer sufficient. The circulation is linked to the state of Arctic sea ice, to the melting of the Greenland ice sheet, to shifts in the structure of tropical Atlantic trade winds, and, according to some studies, even to processes in the Southern Ocean around Antarctica. The planet's ocean isn't a set of independent parts, it's a single interconnected system in which a change in one region can, even with a delay of years or decades, echo in a completely different corner of the globe. One of El Niño's most remarkable features is just how far its influence travels from the epicenter of the event in the tropical Pacific. Scientists call this effect a teleconnection, a link between climate processes unfolding in regions far apart from one another. When the trade winds weaken and warm water shifts toward the eastern Pacific, it isn't just local weather that changes. The position of major zones of rising air in the atmosphere shifts too, and with them, the paths of the jet streams across both hemispheres. The west coast of South America, normally dry thanks to the cold Peru current, sees torrential rain and destructive flooding during strong El Niño events. Indonesia and eastern Australia, by contrast, slide into drought, sometimes severe enough to trigger widespread wildfires. The western Indian Ocean, during El Niño, becomes a stage for stronger tropical cyclones, dumping heavier rainfall on the coastlines they strike. None of these events happen simultaneously or with equal intensity in every cycle. The strength and character of each outcome depends heavily on the specific parameters of that particular El Niño. But the stronger the event, the more confidently forecasters can speak about the probability of particular deviations from normal in a given region. According to NOAA, the probability of a very strong El Niño in November through January of 2026 to 27 was estimated at 63%. An event of that magnitude would rank among the largest since systematic observations began in 1950. Even the most powerful El Niño events don't produce identical outcomes in every region with perfect precision. But statistically, they noticeably shift the odds towards certain scenarios. And that's exactly what allows weather services to prepare farmers, port authorities, and emergency management systems in advance for likely departures from normal conditions, whether that means drought in one region or flooding in another. There's another, slower and less visible process running alongside all of this, accompanying the ocean's warming acidification. Over the past 2.5 centuries, the ocean has absorbed not just excess heat, but a significant share of the excess carbon dioxide entering the atmosphere from burning fossil fuels. The ocean is thought to have absorbed roughly a third of all the anthropogenic carbon dioxide humanity has emitted since the start of the Industrial Revolution. When carbon dioxide dissolves in seawater, it forms carbonic acid, which gradually lowers the ocean's pH, making it slightly less alkaline, slightly more acidic. The change might sound small, fractions of a unit on the pH scale, but for marine organisms that build their shells and skeletons out of calcium carbonate, that difference is directly felt. More acidic water makes it harder to form calcified structures, and in some cases can actually dissolve shells and skeletons that already exist. This affects not just tropical corals, but cold water corals in the deep ocean, oyster farms, and certain plankton species that form the base of the marine food web. Acidification and warming rarely act in isolation. They compound one another, and it's precisely this combination of stressors that makes marine ecosystem responses so difficult to forecast with precision. A coral reef already weakened by heat stress bleaching becomes even more vulnerable to acidification, which slows its ability to repair its damaged skeleton. Behind all of these processes sit very concrete economic figures. By combined estimates from several international studies, coral reefs provide humanity with services worth roughly $9.8 trillion annually, accounting for coastal protection from storm surges, fisheries support, tourism, and even pharmaceutical development based on compounds found in marine organisms. Global fisheries, much of which depend directly or indirectly on the health of coastal ecosystems, provide food and livelihoods for hundreds of millions of people worldwide. That's exactly why the changes happening in the ocean aren't some abstract scientific discussion of interest only to specialists. This is a matter that touches food security for coastal nations, the resilience of coastal cities, the routes of fishing fleets, and ultimately, the well-being of millions of people whose daily lives are tied directly to the sea. And since we're already talking about depths that light can't reach, it's worth telling the story of one of the strangest discoveries of recent years, a discovery the researchers themselves initially refused to take seriously. In 2024, a team of scientists led by Professor Andrew Sweetman of the Scottish Association for Marine Science was working in the Clarion-Clipperton Zone in the Central Pacific at a depth of about 4,000 meters in complete darkness where not a single ray of sunlight ever penetrates. The seafloor there is scattered with rounded metallic nodules about the size of a potato, formed over millions of years as manganese and iron precipitate out of the water around a hard core, a fragment of fish bone, for example. The instruments recorded something that contradicted everything scientists thought they knew about the origin of oxygen on Earth. Oxygen concentration inside sealed experimental chambers on the sea floor wasn't dropping, as expected from the respiration of bottom-dwelling organisms. It was rising in complete darkness with no photosynthesis involved. The researchers found their own data so hard to believe that they initially blamed it on faulty equipment, but the effect kept repeating. Scientists proposed a hypothesis. The metallic nodules themselves might be capable of generating electrical voltage. Measured voltage on the surface of individual nodules reached nearly 1 volt, and when clustered together in sufficient numbers, they could function like a natural battery, capable of splitting seawater molecules into oxygen and hydrogen through electrolysis. If confirmed, this would challenge a centuries-old belief that complex life on Earth only became possible thanks to oxygen produced by photosynthesizing organisms using sunlight, roughly 2.7 billion years ago. The discovery sparked not just scientific excitement, but a sharp debate, one with very real economic stakes attached. The research was partly funded by a Canadian deep-sea mining company planning industrial extraction in that exact zone of the Pacific. Other research teams, responding to the original publication, raised a number of methodological concerns. Previous comparable studies in nodule-rich regions hadn't observed oxygen production. The proposed electrolysis mechanism lacked a clearly demonstrated energy source at the necessary scale, and the recorded rise in oxygen concentration could be explained by an experimental artifact rather than a genuinely new geochemical process. In April 2026, the journal that had first published the results added an official editor's note, alerting readers that certain aspects of the paper were under review by the editorial board. This is yet another perfect example of what science actually looks like from the inside, not a smooth sequence of confirmed facts, but a living process full of debate, rechecking, and temporary question marks. In parallel, other research teams independently discovered that certain groups of deep-sea microorganisms are capable of producing oxygen through an entirely different, purely biological mechanism tied to nitrate processing, adding yet another layer of complexity to understanding where oxygen in the ocean's darkest corners actually comes from. Regardless of whether the electrolysis hypothesis for the nodules holds up, the very existence of this finding raises a question that extends far beyond planetary science. If oxygen can form in complete darkness under high pressure with no photosynthesis at all, could similar processes be happening at the bottom of the ice-covered oceans on other worlds, under the frozen crust of Europa, a moon of Jupiter, or Enceladus, a moon of Saturn? The question remains open. And that's exactly why the debate over dark oxygen follows scientists not just in oceanographic circles, but in astrobiology circles as well. There's also a more practical dimension to this story. The very same nodules at the center of this scientific dispute are simultaneously the object of growing interest from mining companies eager to access the metals they contain: cobalt, nickel, copper, manganese, needed for electric vehicle batteries, wind turbines, and solar panels. Some studies show that regions rich in these nodules host surprisingly high biological diversity, by some estimates exceeding that of certain stretches of tropical rainforest on land. That poses a difficult question for the scientific and international regulatory community: how to weigh the need for metals critical to the energy transition against preserving an ecosystem that humanity, remarkably, still knows very little about. The International Seabed Authority and the United Nations Scientific Advisory Board have already discussed the dark oxygen discovery as one of the factors that must be considered in drafting international rules for deep-sea mining. One more example of how a fundamental scientific question directly shapes real political and economic decisions being made right now. Up to this point, the conversation has focused mostly on the Northern Hemisphere, the cold patch off Greenland, the weakening of AMOC. But the planet has a second mirror image story unfolding on the opposite end of the globe, around Antarctica, and it's far less studied, even though it may prove no less significant. Around the icy continent, on the continental shelf, the ocean's densest, coldest water mass forms: Antarctic bottom water. The process works like this. When sea ice forms around Antarctica each winter, salt is squeezed out of the freezing water, making the water left beneath the ice even saltier and denser. This heavy, cold, salty water sinks along the continental shelf all the way to the ocean floor, then slowly spreads across every ocean basin on the planet, forming the lower branch of the global overturning circulation, the very same system that, viewed from the opposite pole, looks like AMOC. Antarctic bottom water is the single largest water mass on Earth, making up 30 to 40% of the entire volume of the world ocean. It plays a key role in absorbing heat and carbon on multi-century, even millennial timescales. And in recent years, something strikingly similar to the AMOC story has been happening to this water mass, possibly even faster. A study published in Nature Climate Change found that the volume of one of the key varieties of Antarctic bottom water formed in the Weddell Sea and responsible for nearly half of global production of this water mass has shrunk by 30% since 1992, with an especially sharp drop among the densest, coldest classes of water. The cause, it appears, lies in a more than 40% decline in the rate of sea ice formation on the continental shelf, which in turn is tied to shifting wind patterns, partly explained by a phase change in the Pacific decadal oscillation that's been underway since the early 1990s. Another study, published in Nature in 2023 by a team of Australian scientists, used a high-resolution ocean model to show that under a high-emissions scenario, the expected increase in Antarctic ice sheet meltwater will slow the abyssal overturning circulation and simultaneously warm and age the ocean's deep waters. In other words, these waters will spend more time at depth without renewing, losing oxygen and gradually warming. By 2025, scientific consensus on this question had noticeably solidified. A wide-ranging review in Nature focused on abrupt changes in the Antarctic environment stated plainly that the expected slowdown of the Antarctic overturning circulation this century could turn out to be even faster than the projected slowdown of AMOC in the Atlantic. At the same time, the authors noted that the sharp decline in Antarctic sea ice extent, a far more abrupt, nonlinear phenomenon than the comparable loss of Arctic ice, has already pushed the system beyond the range of natural variability seen over past centuries. The record-low Antarctic sea ice extent recorded in 2023 became a striking example of just how quickly changes like this can unfold. That year's June ice anomaly was twice as large as the previous record for that month. A separate study found that this abrupt loss of sea ice has already noticeably altered the pattern of ocean-atmosphere interaction in the Southern Ocean, intensifying both surface heat loss and storm frequency over the region, while scientists acknowledge that the broader, longer-term implications of these changes for Antarctic bottom water formation remain unclear and require further study. An international UNESCO report on the state of the ocean, released in early 2026, openly documented for the first time an emerging scientific consensus. The melting of the Greenland and Antarctic ice sheets may be simultaneously slowing critical ocean currents at both poles of the planet, with potentially serious consequences, from a colder northern Europe to accelerated sea level rise along the U.S. East Coast. It's worth restating, though, the balance of opinion within the scientific community. Not every study paints an equally alarming picture. A paper published in Nature in February 2025, covering 34 different climate models, concluded that AMOC shows resilience even under extreme scenarios of greenhouse gas emissions and North Atlantic freshwater input, and that a collapse of the circulation during the 21st century is unlikely. That study directly contradicts the more alarming conclusions of certain other work. And this kind of disagreement between good faith research teams using different models and different methods illustrates better than words how active and how uncertain this field of research remains right now. That's exactly why the Southern Ocean, long overlooked in public attention compared to the better studied Atlantic, has in recent years become one of the priority destinations for international oceanographic expeditions. Scientists are deploying additional autonomous floats there, including specialized models capable of operating beneath the ice in one of the most difficult-to-reach, least studied regions of the entire world ocean. There's one more tool scientists use today to try to understand whether a major climate system is approaching a point of abrupt transition into a new state: so-called early warning signals, based on a phenomenon physicists call critical slowing down. The idea itself is simple, and it applies to far more than just the ocean. Any stable system knocked out of equilibrium by a small disturbance usually returns fairly quickly to its normal state. But as a system approaches a tipping point, beyond which return to its former state becomes impossible, it starts recovering from random fluctuations more and more slowly, and its swings around the average grow more pronounced. That's critical slowing down, and it can be detected equally well in climate systems, ecosystems, financial markets, and even electrical circuits. An analysis of long records of indirect data on AMOC's condition, reconstructed from sea surface temperature and other indicators, published back in 2021, found exactly these kinds of statistical fingerprints. Over the past century, the system has shown a growing loss of stability, one of the first quantitative signals suggesting the circulation may be approaching a critical threshold. Since then, similar early detection methods for tipping points have been actively developed and applied to a whole range of climate systems, from ice sheets to rainforests to coral reefs. It's important to understand the limits of this approach. Detecting a statistical signature of critical slowing down doesn't tell you exactly when a transition will happen, and it doesn't even guarantee one will happen at all in the foreseeable future. It only indicates that a system is losing some of its internal stability. It's more of a warning sign requiring closer attention than a final verdict. Still, it's the accumulation of these independent lines of evidence, the direct rapid measurements, the temperature fingerprints at mid-depths, the statistical signs of critical slowing down, the paleoclimate parallels with Dansgaard-Oeschger events, that is gradually pushing the scientific community toward taking more seriously a risk that just 10 years ago many considered a low-probability scenario bordering on science fiction. Now, having pulled all these threads together, the cold patch off Greenland, the colossal warm mass in the Pacific, the slowing deep circulation, the fourth global coral bleaching event, a deep ocean losing oxygen, and a mysterious source of oxygen seemingly being born in the pitch black of the seafloor, we can return to the question this film opened with. Why does the ocean, which has stabilized Earth's climate for millions of years, seem to be working differently today? The answer modern science gives is far more interesting and far more honest than a simple, "the ocean is breaking." The ocean hasn't stopped functioning as the planet's climate regulator. It continues to absorb more than 90% of the planet's excess heat. It continues to redistribute energy between the equator and the poles. It continues to sustain the planet's oxygen balance, take part in the carbon cycle, and feed clouds, storms, and monsoons with its moisture. But individual mechanisms within this enormous system are showing signs of shifting into a new state, and it's the pace of that shift that keeps catching scientists off guard more often than they'd like. AMOC is slowing faster than the previous generation of climate models predicted. Marine heat waves are becoming, in certain regions, not a rare exception, but an almost annual occurrence. The deep ocean is losing oxygen, slowly but irreversibly, even under scenarios where humanity stops greenhouse gas emissions today. And in the pitch darkness of the seafloor, where surprises would seem impossible, scientists have found a process that calls into question basic assumptions about the origin of oxygen on this planet. Notice what all these stories share. In each one, the line between an established fact and an open question doesn't sit where you'd expect it to. The existence of the cold patch in the Atlantic is an established fact, confirmed by decades of direct temperature measurements. Its precise connection to a weakening AMOC is still a hypothesis, though one gaining support from a growing number of independent studies. The measured slowdown of the deep circulation by a specific amount over the past 20 years is a direct measurement from the rapid array. The exact percentage by which it will weaken by 2100 is the subject of ongoing calculations, where different methods produce different, though converging, estimates. The existence of dark oxygen as a measurable phenomenon is a reproduced experimental result. The mechanism behind it and its broader significance for planetary science is the subject of an intense, far from settled scientific dispute. This kind of layered distinction isn't a sign of weakness in science. It's actually a sign that science is working exactly as it should, constantly checking itself, refining its estimates as new data arrives, and not being afraid to publicly revise its conclusions when new observations demand it. There's one more thing tying together every story in this film: the growing role of an observation infrastructure most people never think about in their daily lives. 4,000 autonomous Argo floats drifting across every ocean on the planet. Satellites measuring sea surface height to within centimeters every single day. The rapid mooring stations continuously measuring the strength of the current across the Atlantic for more than 20 years running. Autonomous underwater vehicles descending 4,000 meters into total darkness that, until recently, only a handful of expeditions ever dared to explore. It's this infrastructure, largely invisible to the public, that makes it possible to even ask the questions this film has explored, and to get answers grounded not in guesswork, but in data. It's also worth noting just how quickly this observation infrastructure itself is evolving. Just 20 years ago, scientists had only scattered point measurements from occasional research expeditions to work with. Today, they get a global, nearly continuous picture of the ocean's condition, from the surface down to 2,000 meters, and eventually 6,000. This is a revolution in oceanography comparable in significance to the revolution satellite imagery brought to meteorology. And like any revolution in observation, it brings not just answers, but new questions that were previously impossible to even formulate, because there wasn't enough data to notice them. What does this mean for the future? Above all, it means the 21st century will likely go down in the history of oceanography as the period when studying the ocean became one of the central scientific priorities of the planet, comparable in importance to space exploration or genome research. Every new expedition, every new float, every new satellite adds one more piece to the overall picture of how the largest, most complex, and most inertial part of Earth's climate system actually works. Scientists at the world's leading institutions, from the Scripps Institution of Oceanography in California to the Potsdam Institute for Climate Impact Research in Germany, from the U.S. National Oceanic and Atmospheric Administration to Europe's Copernicus program, agree on one thing. What we're observing in the ocean today calls not for panic, but for close, patient, methodical study. It's that kind of study, not hasty conclusions, that can give humanity a genuine understanding of what's happening and genuine tools to prepare for it. The ocean holds the memory of Earth's climate across millions of years, in seabed sediments, in the chemical makeup of shells, in the isotopic signatures locked in ice. And it remains the primary buffer, continuing to absorb excess heat and shield land from far more violent temperature swings than the ones we're seeing now. The question that remains open, and that will shape the scientific agenda for decades to come, isn't "has the ocean broken?" It's something far more subtle and far more interesting. How quickly are the individual mechanisms within this system shifting into a new state, and what will that actually mean for the planet's climate in the decades ahead? The ocean remains Earth's primary climate regulator, but current research, from buoys in the North Atlantic to autonomous floats 4,000 meters deep in the Pacific, shows that some of its mechanisms are changing faster than scientists expected even 10 years ago. That's exactly why studying the ocean is becoming one of the most important scientific undertakings of the 21st century, an undertaking whose answers keep arriving right now, even as you watch this film.